Hi, my name is Rosie Gusky. I'm working with Chris Barnes and Chris Butler. We're designing a unified logic analyzer and oscilloscope with our sponsor company Cypress, who builds a microcontroller. This device will be a piece of test equipment available for electrical engineering freshmen and sophomores so that they can perform lab experiments outside of lab. Today we're going to walk you through a brief description of our project. Then we're going to show you our block diagram of our implementation and talk about our specifications for our project. After that, we will briefly discuss the future steps to implement our design process, and that'll be it. Thank you very much. I'm going to briefly describe the functionality of our project. Our project is divided into two parts. We have hardware and software. So the hardware is going to be the inputs from signals and a little bit of signal processing, and then outputting through USB to a computer interface. The user interface on the computer is going to have inputs for control from the user, such as when to trigger or which functionality, either oscilloscope or logic analyzer, they're currently running, as well as windows for displaying and saving data from input waveforms. An oscilloscope is used to measure analog signals, and the signals that we're going to input to our oscilloscope will be between -30 and 30 volts. We'll attenuate that signal down to a size that can be read by our analog to digital converters, which will be between 0 and 2.5 volts. We'll then send that signal into our microprocessor, which will facilitate sending it to the GUI, the user interface on the computer, which will process and display the data, save the data, and also send information back to the microcontroller on how to control the data intake process. The oscilloscope is going to have two inputs that can be displayed concurrently, and the logic analyzer will have 8 different logic inputs that can be displayed concurrently. The device will also have one adjustable voltage level output that will adjust between 1.8, 3.3, and 5 volts for use in logic circuits. We also aspire to add a function generator output to the device. So if we get everything functioning and we still have some time, we're going to add a function generator output that will output a signal at 1.8, 3.3, or 5 volts that is either a sine, square, or triangle wave. Thank you.
Hi, my name is Chris Butler. I will be discussing the top-level diagram of our circuit. I will first discuss the enclosure, and then move on to the hardware side of the device, and then discuss the software side of the front end, which the student will use to configure the device. The first block diagram I will discuss is the enclosure. This is the device that a student will receive when they are using the circuit. On the left hand side you can see 2 oscilloscope probes which can be connected via B and C connectors. Below that is an attenuation switch which will choose between 1x and 10x attenuation based on the oscilloscope probes that are connected. Below that are the logic probes, which can be connected to the circuit under test and will be probing the signals that are chosen. On the right hand side you can see a VREG out, which will power the circuit under test. This is choosable between 1.8, 3.3, and 5.0 volts. There are also 3 status LEDs which state the status of the device. The device is powered by USB and has communications to and from the computer which it is connected to. It is also protected against the environment. The next block that I'll be discussing is the inside of the enclosure, that is the USB device. On the left you can see the two inputs from the oscilloscope probes going into an ADC attenuation circuit. This brings down the voltage of the signals to a readable 0 to 2.5 volts by the PSoC 5. There are also 8 inputs from the logic analyzer which are taken directly to the PSoC 5. The PSoC 5 will interpret the data and send it directly to the PC via USB. On the bottom of the circuit you can see a parallel or serial communication with the USB IC which adheres to the standard of USB communication. There are also there's also an LED circuit on the lower left corner, which will indicate the status of the device. The device is also programmed by microcontroller code, as seen on the top of the device, and has a power supply circuit powered by the USB and providing power to the rest of the device, and an output voltage which can power a circuit under test. The last block that I will talk about is the front-end GUI. This is the software that will be installed on the computer. The USB data comes in from the left and goes straight into a data interpreter. This data interpreter will filter data to the appropriate data processing thread. Each data processing thread will then configure the data and output display data to the user interface thread. This user interface thread will then display the waveforms, output a data capture ability, and intake user commands. The user GUI will then process those user commands and then send them to the data interpreter as device settings, which will then configure send the communication to the device.
My name is Chris Barnes. I will be providing the general description of specifications which we will need to adhere to in order to satisfy the needs of the customers, which in our case are the students. These specifications are broken down into 3 categories. The first of which is device and software specifications, which will describe the physical and user interface characteristics provided by the device. The second specification will be the logic analyzer specs, which will involve the technical characteristics provided by the logic analyzer. And last, we'll talk about the oscilloscope specs, which will describe the technical characteristics provided by the oscilloscope. I will start with the device and software specifications. Because the primary customers are students, durability and affordability are key elements to adhere to, which can be done by ensuring that the device costs less than a textbook, as well as withstands and functions through the rigorous daily life of a student, including being dropped and carried in a backpack. It is also important that the customer knows the device is working properly by displaying data in a timely fashion upon the request to begin data capture, which is accomplished by adhering to strict time windows of 60 milliseconds for data presentation to the user. One thing that is important to any user-friendly interface is information retrieval, which will be provided in 3 ways. The user will have the ability to capture the waveform data as either an image or as a .csv file, which will provide the waveform data to the user as numbers on a spreadsheet. The user will also have access to 2 cursors, which will provide differences in voltage, difference in time, and average frequency measurements through the graphical user interface. Finally, the user will also be provided with the waveform data as a decimal, hexadecimal, or binary in a separate window of the user interface. This is especially important for logic analyzer functions, providing a quick and easy way to see that the logic being passed through is correct, since most code is not written in binary. Next, I will talk about the logic analyzer specifications. Bandwidth and sampling rate are important codependent elements. If the bandwidth exceeds the sampling rate, then an entire portion of the signal will pass by without ever having a sample taken. If the sampling rate is greater than the bandwidth but not high enough, then not enough samples will be taken to ensure the full waveform is captured. By limiting the bandwidth to 2 MHz and capturing 10 million samples per second, we can provide the user with 5 samples per period of their waveform, ensuring we capture and present to them the rise and fall of the logic level at the correct time. It is also important that normal logic voltage levels are able to be read by the device, which is accomplished by allowing input signals to be between 1.8 volts and 5 volts. Last, I will talk about the oscilloscope specifications. Bandwidth and sampling rate for the oscilloscope follows the same principles as the logic analyzer, but are more important since the waveform can have more values over a given period than just a 1 or a 0. By providing a larger gap between the bandwidth of the 100 kHz and the sampling rate of 700,000 samples per second, at max frequency we are able to capture 7 samples per period. It is also important to note that most college students will not exceed this bandwidth within their first 3 years, so customer satisfaction is still accomplished. The oscilloscope will also provide input voltages between negative 30 volts and plus 30 volts, which most college students will also not exceed within their first 3 years. Since most students are given 1x or 10x probes to use in classes, these will be fully compatible on our device. That concludes the specifications portion of our presentation.
I'm going to describe the timeline for future work on our project and then conclude our presentation. This term we will finalize our block design, including hardware, pseudocode for the microcontroller, and pseudocode for the PC interface software. We'll also write a test plan with parameters for each block in our block diagram, passing or failing. At the beginning of next term, we'll implement our code, debug, and test the code. We'll also implement our hardware design on a breadboard, and when we get it working, we will implement that on a printed circuit board. We'll then integrate the software and hardware into a single device and test. So today you heard us present our concept design to you. We showed you a high-level block diagram, and we discussed our engineering specifications and how we will implement our work plan. Thank you very much.
Go Team 17!